So we're going over new applications of L'Hopital's rule. So there are situations when you may want to, or you may need to, apply the rule more than once, like in this example. Here, suppose you wanted to compute your limit using or applying L'Hopital's rule, and you arrive at an expression again where both top and bottom vanish at the point. Then that means that the hypothesis of L'Hopital's rule apply again, and you can iterate this and do it as many times as you need before you can just apply the limit laws and obtain the limit directly by simply evaluating. So let's see what happens in this case. This is the actual situation we're in now. So here the top and the bottom both vanish as x approaches 0. So cosine of 0 is 1. So 1 minus 1 is 0. E to the 0 is 1. Minus 0 minus 1 is 0 as well. So we can apply L'Hopital's rule here. And we can compute this limit by taking derivatives of the top and the bottom. And the derivative of the top is e to the x minus 1. The derivative of the bottom is minus sine x. Now as x goes to 0, sine of x goes to 0. And e to the 0 minus 1 goes to 0 as well. So we may apply L'Hopital's rule yet one more time and compute this limit as the limit as x approaches 0 of the derivative of the top. What is the derivative of e to the x minus 1? It's just e to the x. Just e to the x. And the derivative of the of minus sine of x is minus cosine of x. And now we arrived finally at an expression that is continuous at 0 and for which the denominator doesn't vanish. So we can compute this limit by simply evaluating at the point x equals 0. So e to the 0 divided by minus cosine of 0 is equal to 1 over minus 1, which is just minus 1. And as I said, one can iterate as many times as necessary. But we need to always check the hypothesis before any new application. Okay, so that's what happens when you need to iterate the rule. And now we are going to go over a few other forms that can be tackled using the same technique. So we've seen what happens when you deal with expressions of the form 0 over 0 or 0 times infinity. Now we also have expressions such as infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to 0. You still have competing effects, like infinity minus infinity could be anything. I mean, two quantities that are growing very fast and you subtracting them, one can go to infinity much faster than the other one, so they might lead to infinity or minus infinity, or they could both be the same quantity basically, and then you get 0. So the same happens with 0 to the 0, 1 to infinity, or infinity to 0. You don't know from the expressions what you're going to get. Okay, so you need to apply something. And as we said in the first video for the L'Hopital's rule technique, we will do so by reducing everything to the form something divided by something, which is the first application. So let's see this in examples. So of the form say infinity minus infinity. So this is what happens when, for instance, you would like to compute the limit as x approaches 0 of 1 over sine x minus 1 over x. Okay, so what do we do in this case? We cross multiply and transform this into a fraction. So this would be x minus sine of x divided by the product x times sine of x. Here we started from an expression that is approaching infinity minus infinity, depending on whether you are on approaching 0 from the right or from the left. And the same thing with this expression here. 1 over x is approaching either plus or minus infinity, depending on whether you're approaching 0 from the right or from the left. So this is the form infinity minus infinity. And we rewrite this expression here to get a quotient. And now this quotient is in a familiar form. So x times sine x approaches 0 when x approaches 0, and so does x minus sine x, because each one of the terms approaches 0 individually. So we can apply L'Hopital's rule now. So this is the same, this will be the same as the limit as x approaches 0 of 1 minus cosine of x divided by the derivative of the bottom, which is sine x. So we need to apply the product rule, plus x times the cosine of x. And in fact, we find ourselves in a situation like in the previous example, where if we try to plug in 0, we get 1 minus cosine of 0, which is 0, divided by sine of 0, which is 0, plus 0 times 1, which is 0. So both the numerator and the denominator vanish at the same time when x is equal to 0. So we may apply L'Hopital's rule once again to get that limit of this expression is equal to, what's the derivative of the top? Is sine x, so the derivative minus cosine, and the derivative of the bottom is, well, the derivative sine of x is cosine x. We need to apply the chain rule. Cosine x times 1 plus x times minus sine of x. Okay, and what happens here? Well, sine of x is approaching 0. Okay, well, so can we apply L'Hopital's one more time? No, we have to check what happens with the denominator. Here we get 2 cosine x, which is approaching 2. And this expression here, the x times minus sine x, is approaching 0. So you're gonna get that this whole thing, the bottom, is approaching 2, as it's approaching 0. So you have a continuous expression here, and you don't need to apply L'Hopital's rule again. The top is approaching 0, but the bottom is approaching 2. So we can safely evaluate here and plug in the value 0, and we get 0 over 2, which is just 0. Now, for the other two forms, like, no, for the other three forms, when you have, say, 0 to 0, 1 to infinity, and infinity to 0, we're dealing forms. We are dealing with expressions like f of x to the g of x. So, and if you remember, the advice I gave you for the previous section, in this case we take the natural log natural, so let's say we apply natural log, so an ln, and deal with that. So suppose we want to compute, suppose we want compute the limit of y as x approaches a, where y is f of x to the g of x, and f of x is approaching, say, 0, so x approaches a, and g of x approaches 0 as well. Then we instead find the limit let's find the limit natural log of y, which is equal to the limit when x approaches a of g of x times the natural log of f of x. Remember that the natural log of f of x to the g of x is g of x times the natural log of f of x, no, to f of x, that's right. And now this expression here leads to an indeterminate form of the type, this is going to 0, and natural log of 0, which is going to minus infinity. So we already know how to compute that. And so once we know the limit of natural log of y, then the limit of y can be computed as the limit as x approaches a of e to the natural log of y. Remember that y is the same as e to the natural log of y. And so, and since e to the something, e to the x is continuous, we can bring the limit inside. This is the same as e to the limit of natural log of y as x approaches a. And so this is what we compute using L'Hopital's rule. And at the very end, we raise e to that quantity, and that gives us our limit. Okay, so one first example. So let's try to see this principle in the following example. Okay, how do we deal with expressions like this? So from the previous section, what would happen if we were asked to find the limit as x approaches 0 plus x to the x? So everything we've said so far for the L'Hopital's rule also applies when you have one-sided limits. Okay, so you can do that, no problem. Just like when we have derivatives or continuity, we can apply all those principles with the obvious modifications, we can do that as well in here. So here the limit of x to the x as x approaches 0 plus leads to an indeterminate form of the type 0 to the 0. So it's not clear what this is approaching. So what do we do? So this is our example. Here we say we're interested in the limit of y. So we take the natural log. So this is the first step. Take the log. Take the natural log, and we get x times the natural log of x. And we compute the limit. Then the limit as x approaches 0 plus of x times the natural log of x. Oh, but we already know what this is. So we computed before. And this is equal to 0. Just check the previous examples. We obtained this limit using L'Hopital's rule. Remember, we wrote x times natural log of x as natural log of x divided by 1 over x. And we apply L'Hopital's rule here. And we got that this was equal to 0. The limit is equal to 0. So that means that the natural log of y goes to 0. Natural log of y is x times the natural log of x. And this implies then that e to the natural log of y, which is equal to y, so y is equal to e to the natural log of y, is going to e to this limit, which is 0, as x approaches 0 plus. So this is approaching 1. So that means that x to the x is approaching 1. So the part where we take exponentials here, once we've computed the limit of the natural log, this is the second step. This is our second step. So first take the natural log, compute the limit of the natural log, and then take the exponential at the end of the limit you obtained. And then again, there are other applications we can go over now. Like this is one. This is a very important one. Well, let's stop first. Do one more example. Let's try to compute the limit when x approaches 0 of 1 plus x to the 1 over x. This something of the form. This is an indeterminate form of the type 1 to the 1 over 0, which is 1 to infinity or minus infinity, depending on which side of x you are. Okay, so how do we compute this? Remember, first step, take natural log. So we get the natural log of 1 plus x to the 1 over x, which is 1 over x. Remember, this is an exponent, so it comes down. Multiplying, this is times the natural log of 1 plus x. Okay, and then we compute this limit then. Limit when x approaches 0 of 1 over x times the natural log of 1 plus x. And this is, sorry about that. This is a perfect situation for L'Hopital's rule, because natural log of 1 over 1 plus x natural log of 1 plus x approaches 0 as x approaches 0 because you get natural log of 1, which is 0, and x, well, x is approaching 0, which is a given, okay, which is the denominator. Okay, so we can apply L'Hopital's rule here. And we can compute this limit as the limit as x approaches 0 of the derivative of the top, which is 1 over 1 plus x, divided by the derivative of the bottom, which is minus 1 over x squared. And this is the same as the limit as x approaches 0 of minus x squared divided by 1 plus x. And this is a very nice expression. Continues, and the denominator doesn't vanish at 0, so we can just evaluate it, which gives us 0 minus 0 squared divided by 1 plus 0, which is just 0 in the end. And we've done the first step. We took natural log and computed the limit of log. And the second step, what is our limit? 0, so we need to take the exponential of that. Okay, so the limit of 1 plus x to the 1 over x as x approaches 0 is just the e to the limit we obtained before, and that is equal to 1. Yeah, I hope that's clear. The only okay, so let me go over this whole thing again. Whenever you're dealing with expressions, not only for the application of L'Hopital's rule, but in general, when you're dealing with expressions like f of x to the g of x, it's always wise to take the natural log before doing anything else. In this example, in these couple of examples, whenever we're asked to compute a limit involving an expression of the form f of x to the g dx, we took the natural log first and then computed the limit of the natural log of that expression. And then we applied L'Hopital's rule to compute the limit of the natural log, like in this example. And like in the example, like this example here. So we computed the limit of x to x times natural log of x. We actually computed it before in an earlier example. And then at the end, we just need to take exponentials, and the limit is going to be just e to that limit that we find. Okay, so that's about that. The last thing we need to learn now is limits at infinity. And we'll continue in the next video.